Right level. 30 seconds. Contact light. Okay, engine stop. Both control, both autos, engine command override off. Engine arm off. 413 is in. The Eagle has landed.
69 disguised the fact that his heart rate had tripled on the descent to the moon's surface. At the time, commentators conveyed a relief, excitement, pride and disbelief that many people experienced. Though they could see the pictures of Aldrin and Armstrong walking on the moon, some couldn't accept it was happening, convinced themselves it was a televisual hoax, with stage sets and actors hopping around like space-suited kangaroos. But why did we go to the moon at all? Aside from the nationalistic reasons, did the Apollo program serve any useful purpose? Apart from the simple challenge, there were also questions that tantalized mankind for centuries. How were the sun and the earth made? How was the moon made? And when? And what about the other planets in the solar system? And perhaps the ultimate question, is there life elsewhere? It all began on July the 21st, 1969, with that dramatic moon landing. The Apollo astronauts, in addition to planting flags and playing golf, returned with nearly half a ton of moon rock, which scientists from all over the world fell to analyzing. One of the chief investigators was Jerry Wasserberg. I asked him, what have we learned from the moon?
What it's told us is the most important thing is process. What are the processes that govern the phenomena which you're observing? The moon was our first planet where we could see the processes. These were the cosmic processes of the bombardment of the surfaces of a planet which had been undressed to cosmic forces because it has no atmosphere. There's a vacuum. So when we look at the planet, we now understand, this is what actually happens out in space rather than guessing what things would be like. And this is now our baseline for all intelligent discussions about what happens elsewhere in the solar system or the cosmos. We also have been able to determine the time scales over which the processes have acted. Now, for example, we know that volcanism, which one can tell by simple inspection of a lunar rock, took place over a time scale which represents the more ancient part of the whole history of the Earth. The average age of a rock on the Earth, if you include the ocean bottoms as well, is maybe 200 or 300 million years old. Whereas the youngest material which we have ever found on the moon is a little over 3,000 million years old. So it's at least a factor of 10 older, and we then look at a very peculiar planet which was quite active in its early history and managed to shut itself off. The volcanic activity which floods the basins in the moon, which you can see with your naked eye, and certainly even with my bad vision with a pair of binoculars, the black material which flooded these basins, which were created by impacts, this black lava spewed out somewhere between 3.8 and 3.0 thousand million years ago. Call 1,000 million years an eon, since it sort of has a kind of cosmic significance. Now, the holes in the basins they fill represent major impacts, and the general surface of the moon, which is in fact highland area, which is the stuff simply not flooded by these seas of lava, were apparently also formed by the most recent major bombardment about 4 eons ago. These highlands also contain material close to the age of the solar system, namely 4.5 eons old. The history then that one's constructed for the moon is that the moon must have been formed about contemporaneous with the Earth, and was then subject to a history of bombardment after its formation, which culminated in a very massive bombardment at about 4 eons ago, subsequent to which the heavy shooting stopped, which must have also involved the Earth, and may explain the absence of many features on the Earth which are truly ancient, and then began a rather quiet flooding, probably triggered by the last major blast of incoming 50-kilometer billiard balls that were hitting us all. Now, one had a footprint on the moon, which one can't see in the Earth directly, of major bombardment at around 4 eons. So one's transposed this as a time scale of the other planets where we have no direct evidence. And so now every time one goes out with a spacecraft and sees a planet that's shot up with big billiard balls, you say, And the time scale on this other planet is now 4 eons, and so that's how we may judge time.
The major disappointment of the Apollo program was that despite the billions of dollars expended, we still don't know how the moon was formed. But as Joey Wasserberg says, we do know the moon was heavily bombarded by 50-kilometer diameter billiard balls. It seems likely that this salvo was not unique to the moon. The whole solar system was a vast shooting gallery, and so we can feel confident any heavily scarred planetary surface is at least 4 billion years old. This was certainly true for Mercury, the innermost of the rocky terrestrial planets, as we discovered in 1974 when Mariner 10 gave us our first prolonged close-up view. In the mind of veteran geologist Hal Mazursky of the U.S. Geological Survey, the Mercurian photographs evoked a strange feeling of déjà vu.
If you look at pictures of Mercury, they look so much like the lunar ones that some people are confused by them. There are certain subtle distinctions that allow you to recognize them. In other words, the surface looks as though it has been heavily impacted, and there are, in addition to the small craters, there are enormous craters. There's a so-called Caloris Basin, and it's as big as the largest impact basins on the moon. Mercury has no atmosphere, so like the moon, the only thing that disturbs the older craters are the younger craters.
So in terms of dating events in the solar system, were we surprised to find such a heavy cratered object so close to the sun?
No, because in each of the bodies that we've seen, there seems to be a very early episode of extremely high flux, that is, many, many objects striking the surface. And that's called the sweeping up process. Then the rate seems to be almost constant since that time. And what that means, we're gradually sweeping up to much more dispersed objects. So there was this very early period of very intense bombardment, and then a long, slow, gradual decline since. And that seems to be true in each of the bodies that we've studied in detail.
So although Mercury, should we say, is moon-like on the outside, what about on the inside? Is it still moon-like?
There are some very significant difference because the gravity is higher. It must have a very large core.
So in some respects then we have a sort of a hybrid body of an Earth-like interior and a lunar-like exterior.
It's Earth inside and Moon out.
Other bodies in the solar system, the other one with a very thin atmosphere that we looked at in some detail has been Mars. What is the current feeling that we have towards the surface of Mars now that we're still looking at today with Viking?
Well, Mars turns out to be a much more complicated planet. That is, there are many more geologic processes because there is the atmosphere. Not only is there an atmosphere, but it has changed radically through time. So we see the evidence for times in the past when Mars apparently looked very different from the way it does now. And in this sense, it's very much like the Earth, because the Earth has changed radically through time. The most obvious difference on the Earth is that we're living at the end of the Ice Age. And there were enormous glaciers just a few thousand years ago. Most of the Earth's history, it's been much warmer, and there have been no ice caps. So we're seeing the Earth in a very unusual time. And apparently we have a similar unusual time on Mars, because Mars has polar caps also.
So in fact we're looking at Mars now in the middle of an ice age?
Yes, it looks to be the case. There are large polar caps in the north and south. They advance and retreat during every Mars year. But we see on Mars the evidence for channels that look as though they were carved by running water. There are two things wrong with Mars now. Number one, it's so cold that the water would freeze. Number two, the atmosphere is so thin that if you put water on the surface now, it would explosively evaporate. So it would disappear immediately.
So you're suggesting, in fact, that Mars in the past may have had a much more pleasant climate?
Well, it has to have, unless we are mistaken about the origin of the channels. If the channels were formed by some other process, then that wouldn't be the case. But a great many people have debated this issue, and I think the very strong consensus view is that these channels were carved by water running on the Mars surface. Not only that, but it didn't happen one time. It seems to have happened many times during Mars history. We've spent a great deal of time counting craters on the floors of the channels. And the great debate that goes on now is how does that cratering rate tie into actual dates? Our only basis for putting dates on other planetary bodies is by study of the moon. We returned rocks and dated them by radioactive methods. Now we can compare the craters in those regions and build up a time scale. So we've done that, And we can put dates on the Mars channels and the Mars volcanoes because there are big volcanoes that erupted at different times. Some of them are heavily pockmarked with craters and are very ancient. Others have almost no craters, so they're so young that crater counting doesn't work. So what we're trying to do now is put the history together to say when the volcanic episodes were, when the times of mild climate.
So in fact the next step would be what? To bring back some sample from Mars, do you think, and use that in some analysis?
We think that's the next way we're really going to make progress. If we did that, landed several different places, then we could build up a time history. Now the reason that we think is important is that we have decided that there are many episodes of volcanism and glaciation on the Earth. And some of these go back into very, very ancient times, back in the Precambrian, before there was life on the Earth. And we've not decided what makes glaciers or ice ages on the Earth. I think there are 23 people that have written about it, and there are 23 ideas. Now, what we'd like to do then is bring the samples back from Mars and date their ice ages. Then we plot these, and we plot the Earth's ice ages. If they match up, then we say, aha, it's differences in the solar output. That sometimes the sun put out more energy, other times less, and the two things are going together. And that would be the only thing that we think would cause the times to exactly match. If they both have totally different time scales, then we say, well, the heat engines ran at different rates at different times, and so the Earth has its own story, and Mars has its own story.
On the Moon, Mars and Mercury, we can read the surface history directly, but this is not the case for Venus. Only recently have we been able to penetrate its thick clouds, using radar to form images of the terrain below. I asked Hal Mazersky, what does Venus look like beneath the clouds?
Well, it turns out that Venus is very interesting. What we call the Great Northern Plateau turned out to be as big as Australia, so we're now calling it the Northern Continent. And that continent has big mountains along two edges and a great mountain range in the center. Now, that plateau is twice as big as the Tibetan Plateau. That's the biggest, highest one on the Earth. The one on Venus is a bit higher, and it has those big mountains, and those mountains are as high as Mount Everest. So we have some very big features. We've just seen another great continental mass near the equator, and that one is as big as Africa, and it has mountains much higher than any on Africa. So we have at least two big continental areas that we've seen so far. We have one other mountain chain, and it looks like there's a great fracture zone and then two big volcanoes along it. The size and shape of them looks similar to the great volcanoes on the Earth. Now, the Soviets landed two spacecraft just east of that mountain range, and they gave a chemistry which is crude, but it looks like it's basalt. Basalt is the commonest rock on the Earth, on the Moon, on Mercury, Mars. It looks like it's very common on Venus also. And we would have guessed from the shape of those volcanoes that they were basaltic in composition. So we were delighted with the Soviet measurements that said, in fact, that seemed to be the case. They have one other measurement. There's a great lowland that has craters on it. And we say, well, if it's cratered, it must be this ancient crust that we've talked about. And the ancient crust on the Moon and the Earth are made up of rocks that are high in silicon and aluminum. And they have a composition of granitic rocks. And lo and behold, the Soviets landed a spacecraft there, and the composition turned out to be granitic, just what we would have anticipated from our ideas about the development of the Earth.
As Hal Mazersky has said, the Moon, Mercury, Venus and Mars are all rocky bodies with a chemistry similar to that of the Earth. When we sent the Viking spacecraft to Mars in 1976, we did so with the prior knowledge that the red planet retained a vestigial envelope of gases, mainly carbon dioxide. With the Viking landings, we had the first opportunity to sample its gases directly. Considerable interest focused upon the noble gases, neon, argon, krypton and xenon, which are chemically inactive and have remained unaltered since the formation of the planet. In a sense, they are fossil elements providing us with clues to the state of the early Martian atmosphere. Toby Owen of the State University of New York was one of the Viking experimenters, and he outlined for me the results of these measurements.
One of the most interesting things about those noble gases on Mars is that we found that their relative abundances were virtually identical to the relative abundances of the gases on the Earth. So the amount of neon relative to the amount of argon, krypton, xenon, that pattern of abundances is similar in the two cases, virtually identical. That same pattern is found in the meteorites. Now that made us feel that perhaps the other volatile elements like carbon and nitrogen and oxygen in the form of water would also be present in the same abundance pattern as we found it on the Earth and in the meteorites. So that by using the present abundances of the noble gases, we could calculate the total volatile inventory, the total amount of volatile elements that had been degassed by Mars over time. The noble gases are still in the atmosphere, but we can estimate how to the present atmospheric pressure on the Earth.
And that's, of course, an exciting possibility, because the possibility of liquid water. For how long do you think Mars could have retained an atmosphere like this?
That's, of course, the question that we can't answer yet. But our feeling is as follows. The atmosphere indeed would be dense enough for liquid water to exist. That then presumably was the time during which those channels were cut that look so much like dried riverbeds, and which the large ones at least seem to be very ancient. So there was a time with a dense atmosphere, and that dense atmosphere gradually disappeared. How did that happen? Well, one possibility is that the liquid water, which existed then, would dissolve carbon dioxide, just as the oceans do on the Earth, that carbon dioxide in the water can then interact with the rocks and form carbonate rocks. And once that happens, the carbon dioxide is trapped. It's very difficult to get it out again. And in fact, the only way is to heat the rocks to very high temperatures. To have that kind of thing happen, you have to have a geologically active surface, which Mars simply doesn't have. Therefore, once you lose the carbon dioxide to the rocks, it's gone for good. So the surface pressure then would gradually decline. Similarly, Mars is small enough so that nitrogen can escape from the gravitational field, and that's been happening over time too. We see the results of that in the peculiar abundances of the nitrogen isotopes in the Martian atmosphere.
So what can we look forward to in the future? We've had our paradise lost, we're now in an ice age. Hospitable planet in the future?
I'm afraid not. I'm afraid it's an irreversible decline. I think when we look at Mars, we're looking at a planet that was evidently too small to accumulate a large enough atmosphere to reach some kind of stability. And there's not the geological activity to recycle things to create a steady state. So instead what we have is a planet with a very thin atmosphere, which may undergo small cycles, small changes in the overall pressure, but will never get back to that early paradise.
Of course, the other object, just the planet Venus that we've looked at in great detail, we've managed to sample the atmosphere only a few months ago. What have we learned about the past Venus atmosphere as a result of these studies?
Once again, we went there with some original knowledge, and that was that Venus, like Mars, appeared to have an atmosphere consisting mainly of carbon dioxide. Now, when those discoveries were originally made, people were very puzzled by them because these two planets seemed so different from the Earth. But in fact, if we reconstructed what the Earth's atmosphere would be like in the absence of life on Earth and in the absence of liquid water, abundant liquid water on Earth, our atmosphere would also be over 90% carbon dioxide. So what these two planets seem to tell us is that the Earth is a normal planet, at least it began that way, and the big difference is that it's at the right temperature so that liquid water can exist, it's the right size so that it had a thick atmosphere, and those two conditions allowed life to develop, and that's what brought us where we are. So let's turn to Venus then. Why is Venus so different from the Earth today? Mars, we saw, was small, but Venus is about the same size as the Earth. What we found in more detailed investigation of the atmosphere is that, indeed, it is mostly carbon dioxide. Once again, there's some nitrogen present, but in addition, there are a lot of unsavory things. There are clouds there that make the planet so bright and lovely in our evening twilight skies are composed of sulfuric acid. And there's evidence in the planet's spectrum and in the data returned from the spacecraft of hydrochloric acid and hydrofluoric acid. The surface temperature on Venus is extremely hot. It's hotter than Mercury, above the melting point of lead. And at those high temperatures, these acids are apparently in a stable equilibrium in the atmosphere.
From that, I think we must conclude that there is certainly no life on Venus. A much more likely candidate is Mars. Experience had earlier taught the Russians the difficulty of landing safely on Mars. Even small rocks, invisible from orbit, could wreck millions of rubles worth of equipment. With this in mind, NASA carefully chose two innocuous-looking plateau sites, and two Viking craft parachuted down to different places in the northern hemisphere. The main problem facing the experimenters was how do you search for life when you don't know what it looks like? They had to assume that life, if it existed, would be based upon carbon, as in the terrestrial organisms. After a superlative landing, the biological package set to work. In one experiment, the Viking life detectors fed a sample of topsoil with a nutrient. This concoction was said to be irresistible to the palate of any self-respecting organism. If a Martian microbe began to consume it, then any gases given off during digestion would be picked up by the sensors. The second experiment looked for evidence of organic compounds. Their absence from the red planet would make it extremely unlikely that Mars could sustain life. I asked Jerry Soffen, head of NASA's Life Sciences Division, what's now the consensus view on the question, does life exist on Mars?
I think there aren't many scientists now who would dispute we do not think we have discovered life on Mars or anything resembling it. In fact, the data, particularly the organic data, which substantiates the biology now, indicates there probably isn't life on Mars.
What about in the past? There is certainly geological data that suggests a very different climate. Is it possible that life could have existed at one stage?
Yeah, the problem is the condition that we had set before of water. Liquid water is, of course, the key molecule for all living things. And the condition of liquid water seems to be possible in the geological passage. You put it together. The problem is the absence of any organic today. That's the really problematic things that causes us to really resist committing ourselves to it. Had we found any organic, we'd begin to put the puzzle together. But we found no organic, and I really mean zero. We had a good test. We looked at high sensitivity, 1 part in 1/10 of a million, and did not find any organic molecules on Mars. Now, since Mars is a mixed planet, it blows around and things are moved from one place to another. If there had been any at any time, I would have expected to find some organic. The indications are that probably Mars didn't start as a biological planet. It has similar histories to the Earth, but it probably didn't take off the way the Earth did.
Does this then give us some understanding on the way life developed on the Earth, since we're not finding life on Mars?
That's the reason for the whole program, is to understand the origin of life on Earth. We never, from the beginning, were looking for life on Mars for its own sake. We were looking to try to understand our own origins, we terrestrial beings. And yes, the answer is we know something more about what the pre-biological conditions may well have been. For example, there's some very interesting clay on Mars that apparently have triggered some of those apparently positive results that we got. And our thoughts are now that the formation of organic compounds, amino acids, nucleic acids, probably is very tied up in these inorganic molecules that seem to have memories, that seem to be able to actually align molecules in such a way as to form the long chains that form the organic compounds that we have here. So there's a very careful diagnosis of what the inorganic conditions are that may have led to the biological formation of life on Earth.
If Mars is barren, should we be looking anywhere else in the future in the solar system for some other evidence or possibilities of life?
Well, my private view is I think we've had a look at the best candidate. Jupiter has so much chemistry, we're very likely to learn something from the chemistry of it. I doubt if there's in any of the Jovian satellites or Jupiter itself we're going to find anything that is a self-replicating system. It's caused us to think carefully, what do we mean by life? What really do we mean by when we say life? We certainly don't anymore mean just plain terrestrial life. There was hope perhaps that Titan would be more interesting than it's probably turning out to be because its temperature is so low. But the kind of organic chemistry that we in the 20th century are familiar with is not likely to go on at the low temperatures of Titan and the high temperatures of Jupiter. So it's a reason why I think we've had the best shot at the solar system. And if you asked me to vote today, I guess I'd believe that probably the Earth is the only planet that has life on it.
I agree with Jerry Soffen that the Earth is the only planet in the solar system capable of harboring life. As he says, liquid water is vital, and our world is the only one with significant amounts. 2/3 of the globe is covered in the stuff. Venus is like a cauldron that boiled dry eons ago, while Mars cooled and eventually froze as its atmosphere leaked away into space. Fortuitously, the Earth sits between them in exactly the right place. But how did life begin here? We know that organic matter in the form of carbonaceous meteorites is moving freely around the solar system, raining down all the planets. The raw materials for life are available, but only on the Earth where the conditions are favorable have these precursors of life been incubated in the warm oceans to develop into self-replicating creatures. These carbonaceous meteorites are doubly interesting because they have encoded within them the history of the formation of the solar system itself. They are fragments of planetary matter in an arrested state of development, relics of a time when the solar system was swarming with meteorites and many planets. Jerry Wasserberg and his colleagues at Caltech have done some elegant detective work on single grains from the Allende meteorite which fell in Mexico in 1969.
What's been discovered there is, most astonishingly, the preservation in the Allende meteorite of material which was its precursor from interstellar dust grains which must have formed the stuff that made our solar system, with a time scale planted on it that is so sharp, so rapid, that the current view is that the formation of the solar system was probably triggered by the explosion of a star of about 20 solar masses, which ejected material into a dense interstellar medium of about 1,000 or 10,000 hydrogen atoms per cubic centimeter, that about 1% of this material was left in the normal interstellar medium, partially stirred up, and this then within a few million years, which on a time scale of 4,600 million years is incredibly rapid, condensed to form droplets, hailstones, and within a few million years after that to make small planets. And this discovery actually is mind-blowing. I never thought, for example, I would live to see it, the notion that you would actually have a piece or something that was close to a piece from another star in your hand from 4.6 eons ago when the planets first began to form.
So Wasserberg's analysis shows that a mere couple of millions of years before the Allende meteorite was formed, a supernova triggered the collapse of a giant dust cloud which condensed to form the solar nebula. About 1% of the material remained in a ring around the new star, forming droplets and hailstones which accreted into bigger and bigger lumps until finally we have the planetary system as it is today. Until 1974, we'd only looked at a small amount of matter comprising the terrestrial planets. Over 99% of the total planetary mass resides in the remote giant gas bags, Jupiter, Saturn, Uranus and Neptune. At their enormous distances, they presented a formidable test of endurance to Pioneer 10, which had to run the gauntlet of the asteroid belt before reaching Jupiter in December 1973. The success of Pioneer laid the foundations for the spectacular Voyager mission to Jupiter earlier this year. Toby Owen had some experiments on board, and I asked him, what could we expect to learn from studying the atmospheres of the outer solar system?
When we go to the outer solar system, we're dealing with very large planets, at least two of which, Jupiter and Saturn, may have retained all of the elements in the abundances that existed in the original solar nebula that formed the sun and all the planets. The hydrogen and helium have long since vanished from the inner solar system, but on Jupiter, we seem to see an amount of hydrogen and helium relative to carbon and nitrogen, which is virtually identical with the amount that we find in the sun. We have an opportunity there to travel back in time to, in fact, study conditions as they must have existed in the original solar nebula. They're preserved on these planets. They give us enormous natural laboratories in which certain chemical experiments are being tried over and over again. And some of these experiments are probably similar, if not identical, to the ones that led to the formation of complex organic compounds on Earth, ultimately leading to the formation of life.
And that primitive chemistry certainly relates to the kaleidoscopic patterns of color that we see on Jupiter. The action of sunlight and fierce lightning storms break up molecules, which are then stirred by the atmospheric weather systems to produce clouds of various hues. At first sight, Jupiter with its banded appearance was seen to have little in common with the Earth, but the Voyager mission has told us that their weather systems are remarkably alike. The major anomaly of this system is the famous and mysterious Great Red Spot. There seems little doubt to me, from my own work on Voyager, that the Great Red Spot is a swirling anticyclone, a massive vortex of high pressure, the largest of a whole family of similar features. Its fame is due to its extraordinary longevity and vividness. The great spot's colour, we now know, comes from red phosphorus, liberated by sunlight, acting on chemicals which spiral slowly upwards from the depths of the atmosphere. But I'm sorry to have to report that the great red spot is shrinking, and during the last century has halved in length to a mere 3 Earth diameters. It could be gone within 100 years or so. Beyond Jupiter's cloud tops, there circle 14 satellites, of which the 4 largest were discovered by Galileo. Working outwards from Jupiter, those 4 planet-sized moons are Io, Europa, Ganymede and Callisto, and we knew virtually nothing about them until Voyager flew by earlier this year. With the giant planet, they form a sort of mini-solar system, and so I asked Hal Mazursky, how did these rocky moons compare with the solid bodies of the inner solar system?
The fascinating thing about the satellites of Jupiter is that the whole spectrum of things that we saw on the inner planet are there, only even more so. Because we not only see Callisto, the outermost body, and it looks just like the moon and Mercury, with differences. That is, it's very heavily cratered. The entire surface is saturated with impact craters.
The big difference being, in fact, these large basins, because we're now looking at an icy body with a very low density compared to the rocky bodies that we have on the inner solar system.
Well, the fascinating thing is that we know that on the Earth, if you make a pile of ice that's more than 200 feet high, it'll flow out. That is, under its own weight. If you make it 300 feet high, it flows out, so it's only 200 feet high. Then it'll hold itself up, ice flowing plastically under its own weight. Now, when you make a great big hole by impact on Callisto, the ice flows in and fills the basin up. The great crater made literally disappears, and we can see beautiful signs of ancient impact craters that have filled themselves up by the ice flowage. We see no signs of internal activity. There are no lava flows, no volcanic rocks, no falling of the surface. Let's jump to Io and then put Ganymede and Europa, which are intermediate, in the middle. When we flew by Io, we saw the volcanic plumes. There are active volcanoes on Io now. There were 8 of them going when we flew by the first time. We've looked carefully over the surface and we can't find a single impact crater. That is, the volcanoes are so active and so much material comes out of them that it's spread over the surface and completely conceals the impacts. As fast as the impacts form, the volcanic rocks cover over it. So Io is exactly the opposite of Callisto. Callisto has all external activity, no internal. Io has all internal activity, no external. The other two fit in between.
Can we explain then what we're looking at in Europa? Europa apparently has some internal heating, but we see no volcanoes. We just see long linear features, which may not are interesting to the untrained eye, but what does that tell you?
Well, apparently there have been enough changes, internal activity, so that the crust of Europa goes up and down. And as it goes up and down, it breaks. And it has fractures in it like fractured ice floes floating on the sea. And we think we found maybe 3 craters on the half of the planet that we've seen. It says that some process is going on that's active enough so that almost all the craters are wiped out. So not only does the surface break, but apparently material must come out of those fractures, spread over the surface, and cover over the impact craters. Because Europa doesn't dodge impacts any more than Io does. It's hit just as hard and just as often as Callisto is, and new material must come out on the surface and bury all of the ancient craters.
So when we look at all these long linear features with white interiors, that in fact is ice about to flow out and cover the surface?
I think that what we see there is that ice that has flowed out and spread widely and given us this very bright ice-covered surface. Apparently Europa has the density of the moon, but the outer rim, the outer surface, is icy.
Now we come to Ganymede, which somehow must fit into your story. What do we see there?
It's exactly in between Callisto and Europa. It's startling that each of the bodies fits just in the right place. On Ganymede, the surface seems to be sheared. That is, the fracturing seems to take place under great pressure, so that there are long parallel lines. In some places, the lines interweave and cut off each other. It almost looks like a basket surface where the grooves are interwoven and cross-cutting. That says to us that apparently the surface is being sheared, so this body is almost halfway between. That is, it has many craters And those craters are in some places wiped out by the shearing of the surface. We actually have some craters that are on the old dark crater terrain, and then they're intersected by the younger, brighter, higher standing shear zones, and those cut craters right in two. And we've now found one enormous crater with these rings around it that looks like the impact of a very big, very ancient body. So it looks like Callisto in this sense. There are many other smaller, younger craters that liberally pockmark the surface. So it doesn't have as many as Callisto, but many, many more than Europa. It's just in between, like Mama Bear.
One of the major problems we are left with, it seems, is to agree on the pronunciation of Io. Anyway, we think the volcanism on Io is due to the strong tidal effects of Jupiter and Europa. In addition, Io is bathed in electrical energy from Jupiter's huge magnetic field, which will trap any particles in the vicinity and induce them to give off radiation. An identical phenomenon was found in the radiation belts around the Earth, named after the discoverer James Van Allen of the University of Iowa. Van Allen is still a front-runner in the study of these magnetospheres, and so I asked the man from Iowa, or should it be Iowa, to describe this Jovian magnetism.
It is in some sense almost like a beehive. If you imagine a magnetosphere, you must think of it being full of swarms of particles whose motion is controlled by the magnetic field. So that in some cases the intensity is enormously high, and maybe billions of particles per square centimeter per second, for example. But it's a huge region. In fact, if you think of looking up at Jupiter in the sky, the total dimension of its magnetosphere is greater than the angular dimension is greater than that of our moon or the sun. So it's a huge region in the sky, not visible to the naked eye. The radiation exposure levels in the vicinity of Jupiter are so high that even electronic equipment is damaged if it spends more than a few hours at the most intense place.
Now, how strong is the Jovian magnetic field compared with the Earth?
Well, it's about 4,000 times as great a magnetic moment, as we call it.
You mentioned the immense size of the Jovian magnetosphere. This must mean that some of the satellites must lie inside it. What is the interaction between the charged particles and the satellites?
Well, in the first place, of course, the satellite acts as a big hunk of rock, let me call it, which absorbs particles which hit it. So it tends to sweep out or deplete the population of charged particles. On the other hand, there are various effects of an electrical nature resulting from the motion of a satellite through the planet's magnetic field, which generate voltages, so like a huge electrical generator, and those voltages act to accelerate particles. So a satellite can be, and apparently is, in the case of Io, both an absorber and a generator. So it absorbs certain classes of particles and accelerates other classes, so it has an extremely complex overall effect on the system.
James Van Allen. Earlier this year, Pioneer 11 discovered that Saturn also has a magnetic field, undetectable from Earth because of the planet's rings. Here, the combined interactions of rings, satellites, and magnetic field are far more complicated than anything we've seen before. Until 2 years ago, it was thought that Saturn was unique among the planets, and that it had a set of rings. But in 1977, Uranus was discovered to possess 5 rings, and now unexpectedly in March of this year, Voyager 1 picked up a faint circle around Jupiter. I asked Toby Owen how the Jovian system compared to those of Saturn and Uranus.
It's intermediate in width between the rings of Saturn and those of Uranus. But what's interesting about them is that the rings of Jupiter are closer to Jupiter than either the rings of Saturn or the rings of Uranus are to their parent planet. And we simply don't understand yet why that is the case. On Saturn, we think the rings are left over from the time the planet formed and had a ring of material around it, rather like the ring of material around the sun that formed the planets and satellites. Now, as that ring cooled, the thought is that perhaps condensation of water could have occurred, and you would have perhaps dust grains coated with water, ice. And indeed, we see water ice in the spectrum of the Saturn rings. But comparable theories for Jupiter suggest that it was always much too hot close to the planet for water to condense and make ice. So ice rings on Jupiter seem unlikely, and that's consistent with the idea that the rings are close. They then are the source of the ring, but the question we haven't been able to answer yet is, why do they gather in that particularly narrow region where we see them now as the ring?
Toby Owen's puzzle may have been partially solved by the discovery 3 months ago of a tiny satellite 30 to 40 kilometers across, which sweeps round the ring like a celestial vacuum cleaner, sucking in particles and leaving a clean, sharp edge. This moon is the fastest object in the solar system, orbiting Jupiter in a mere 7 hours 8 minutes at a speed of 63,000 miles per hour. It's likely that in the past there were other such moons, dragged inwards and destroyed by Jupiter's crushing gravity, and that the rings are just the debris. With Voyager safely on its way to Saturn and Uranus, and if we're lucky Neptune too, we can hope for another 10 years of new insights. It's been a marvelous decade of exploration, comparable with the last 10 years of the 15th century. We too have discovered new worlds. Men have landed on the moon, and we've read the record of a cataclysm. We have seen on Mars Paradise Lost, a hell on Venus, and the bizarre procession of the Jovian satellites. And now we can be sure that our planet is the sole cradle of life in the solar system. But perhaps the supreme irony is that despite the billions spent on space missions, the key that unlocked the secret of the birth of the solar system, that in Blake's words enabled us to see the world in a grain of sand and eternity in an hour, this key just dropped in on us from the void, concealed within the meteorite, which Mexican peasants have been selling off to tourists as souvenirs. Goodbye.
The Solar System 70s was presented by Dr. Gary Hunt and produced by Neil Pemberton. And there'll be a second opportunity to hear it at 7:20.